All right. If you are watching this video in spring of 2022, then we are on page 78 of your purple book. If you're watching this video at some other time, I don't know, you're going to have to flip around and find it. We're going to start talking about acids and bases. This is unit 12, our second to last unit of the year. We're almost there. And this is also a pretty short unit, so we're really almost there. We're going to do this. Let's talk about acids and bases. Acids, you can recognize because they have in front of the formula an H for hydrogen. This is because when your acid dissolves in water, it will also dissociate. That's a word we talked about in Unit 11, dissociating, breaking apart. And when it dissociates in water, it breaks into the H's with a positive charge. And then whatever the anion is left over also breaks up in the water. And those H's are called acidic hydrogens. They are the acid, those H plus ions. So then an acid will increase the concentration of hydrogen or hydronium ions. I wrote this backwards, but you'll figure it out. Okay, so then your hydrogen ions are these, your hydronium ions are these. Basically what happens with the hydronium is you get a water molecule, and then there's the dissolved acid hydrogen in the water, and they combine so that then you end up with all three hydrogens together, still the oxygen, and then that positive charge from the hydrogen ion also makes the whole thing positive. So we call that hydronium. Most formulas of acids will begin with an H, and they're going to taste sour or tart. So this is like your sour candies, like Sour Patch Kids, Warheads, that kind of thing, and lemons. And really anything with acid in it, like citric acid makes citrus fruit have a little bit of a sourness or a tartness to it. Meanwhile, bases have an OH in the back. That's an ion called hydroxide. We'll talk more about that in a second. Same idea with the bases. When they dissociate in water, that means that they split apart and you get all these OHs floating around. Those are the base. That's the part that makes it a base. So bases increase the hydroxide ion concentration in water. Remember, when we talk about concentration, we're talking about like a proportion. So we're saying that like there's water, and then we have a higher like proportion or ratio of what's dissolved in the water being this basic ion, the OH, hydroxide. Most of your base formulas are going to end in OH except for ammonia, which is NH3. You may have heard of ammonia. People use it to clean stuff. Usually the household chemical kind that you buy is yellow and it smells like pee, and that's because ammonia is in pee. But if you have like, straight ammonia from a bottle, then it's been like cleaned and purified, and that's why you can use it to clean stuff sometimes. Your bases will have a bitter taste, like soap. Most soaps are basic, and that's why when you get your mouth washed out with soap, it tastes pretty bitter. Or unsweetened chocolate. If you've ever tasted like straight chocolate before it's had sugar added to it, or like cocoa powder, it's actually very bitter. Okay, there are certain ways that we name acids and bases, and we have to follow these like special rules to name them differently than the way that we name other compounds. So we have a little flow chart here that will help us name acids and bases. The practice problems that I'm going to be comparing this to are, if you're again watching this in spring 2022, you're going to have to turn the page. So like right now, the notes are right here with the flow chart on page 78, but the practice chart I'm looking at is on page 80. So you could, if you wanted to, you could kind of fold your book give it a little hot dog fold so that you can see the notes and the problems at the same time. That's optional, obviously, but like here's our flow chart. I'm going to be referencing, here's the problems we're going to be trying. So you may find that useful to give it a little hot dog fold so you can see the chart with the questions in it and the flow chart with the how do we find the answers at the same time. Okay, the first problem in this chart that I'm going to be looking at is just the very first one, H2SE. Okay, so this is where I'm starting. And we got to figure out how to write a name for this formula. So we look at the flow chart. Does it start with an H? Yes, so it's an acid, okay? The H2SE that we're working on right now does start with an H. So yes, it's an acid. Is it binary, meaning there are two elements, or is it an oxyacid, meaning there are three or more elements? Remember, the number of capital letters is your number of elements. So I have a capital H and a capital S. That's two capitals. That's two elements. It is binary. So the way we name it is you have a prefix of hydro, you have a suffix of ic, and then you write the word acid. And then in the middle, you have to write the root for the name of the second element, the root of the second element name. So like we're going to end up writing for this, the prefix hydro. I'm going to skip and leave myself a little bit of space. Okay. The suffix is ic. I need a second word of acid. Basically, this first word is going to be an adjective describing a noun, where my noun is acid and my adjective is hydro blank ic. What kind of acid? Hydro blah, 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 ic. You didn't think this was going to be a grammar lesson, did you? It's an adjective describing a noun. So you got to have a noun there to describe your adjective. So the root of the second element's name is what goes in that blank. For example, hydrophosphoric acid comes from H3P, where P, the element, is phosphorus. The root of phosphorus is just the phosphor part. The US is a suffix, but the phosphor part is the root name. So that's why phosphor goes in that blank if you're doing hydrophosphoric acid. For this question, Se is an element called selenium, spelled like this. Okay, that IUM is a suffix. Like we have a whole bunch of elements with that IUM suffix. Most of them are metals, lithium, calcium, magnesium. That IUM is a suffix. That's not part of the root. We're not going to use that. But the SELEN, selen, is the root of that element name. So instead of hydro blank ic acid, I'm going to fill it in hydroselenic acid. Hydroselenic acid. What kind of acid? Hydroselenic. We're going to do more. Don't worry. Let's try an oxyacid this time. So we're going to look at H2CrO4 is the question that I'm going to be looking at now this time. So I'm now switching gears to this one, H2CrO4. Okay. And coming back over to our flow chart, I'm going to start myself over with all of this. H2CrO4. So first question, does it start with an H? Yes, it does. So I'm looking at an acid, okay? Is it a binary acid again, only two elements, or is it an oxyacid with three or more elements? Well, we've got capital H, capital C, capital O. So that is three capital letters. That's three elements. So we're looking at an oxyacid. 3+ elements where it's H, and then some element, and then O, and then some number. It says we got to check our polyatomic chart and find the thing that's not hydrogen, basically. So we're going to go looking on the polyatomic chart for the oxyacid part, the XO number part, the CrO4 in this case. The polyatomic chart being this thing that's at the back of your book. Again, if you're watching this in spring 2022, there's a copy of this chart on the other side of the periodic table at the very back of your purple book. We're looking for that CrO4, which is on here. It's called chromate. So I'm going to come back to the flow chart. This thing is called chromate. Let's see what we do with this information. it says we need to change the suffix, which would be the part at the end of the word, right? If it's ate, we change it to ick. If it's ite, we change it to us. We have chromate. We're going to change the ate to ick, and then we're going to write the word acid. So we're going to change this ate right here to an ick, and then that will make it chromic acid. What kind of acid? Chromic acid. Chromic is our adjective. We still need our noun acid at the end. So my answer over here is just chromic acid. Please note, okay, please note that for an oxyacid, we do not use hydro. Okay, there's no hydro on an oxyacid. You're only going to use hydro as a prefix if you're doing a binary acid where it's only H and one other element. If you ever are using the polyatomic ion chart to name an acid, you should never, ever be using hydro with anything that's on this chart. Hydro only goes when you're just using hydrogen and one other element. And that is, by the way, the hydro is for hydrogen, not for water. So there are some examples here as well, just in case we need them, where notice both of these have an oxyacid, hydrogen, and two other elements, 3+ elements total. It's not a binary acid. Binary means two, right? There's more than two elements here. Where there is no hydro in front of the acid name. It's not there. No hydro in front. Not doing it. No hydro. And they changed the suffix us and ick based on if the original ion was called ate or ite. So this one was phosphite, became phosphorus. And yes, they put the whole root of phosphorus back in there. Although if you just wrote phosphus, I would still accept that. Phosphate becomes phosphic, or again, we actually end up putting the whole root of phosphorus back in there. Phosphoric, again, if you put phosphic, I would still accept it. I would just cry a little bit about it. Okay, let's try some more. We're going to try going backwards this time. So now I'm going to look at this one. Okay, carbonic acid. And I know from the word acid, if it's an acid, then it has to start with what letter? We know that all acids in our acid formulas, at least in this class, have an H in front. There's an H in front if it's got the word acid. So I'm going to definitely start with an H because the word acid is telling me this is what kind of compound it is, and acids are going to start with an H. Now I need to decide if this is binary or not. And the way you're going to decide that is by looking to see, did they write the prefix hydro, or did they not? They did not write hydro. So that tells me, looking back over my flow chart, let me erase the previous problem off of here. Okay, the problem we're looking at, carbonic acid does not have hydro. And when it does not have hydro, it's going to be an oxyacid. So I'm going to have to go looking for some kind of ion off of the chart. So if I look at this word carbonic, okay, I know that this ick suffix should have been something else when it was on the ion chart. So I'm going to look at what the rules about suffixes are. The suffixes say that an ick would have come from ate. So this word carbonic, before it became an acid, this was just carbonate. Because the ate turned into an ick when it became an acid, when this joined up with the hydrogen. And So now we're going backwards. Okay, so now we need to go check our polyatomic chart and find carbonate and find the formula for carbonate. So I go looking for the word carbonate on here. And I find the word carbonate. It's CO3 with 2 minus, which we're going to come to a second for what that means. But for now, I'm going to write it down. It's CO3. It's got a -2 charge. We have not charge balanced since December, but we got to go back to doing it. Luckily, very easy to do when one of your charges is hydrogen. So the hydrogen is +1. And if your carbonate has 2 minuses and your hydrogen has 1 plus, and we got to make sure all our pluses have a partner minus. Take your plus and your minus, and you need a second plus to go with that second minus. So we're going to need 2 hydrogens to go with this 1 carbonate. This is coming back to you from December. What we're going to end up writing is that we've got the H, we've got the CO3, but we need 2 H's for the positives and the negatives to balance each other out. We're going to do one more. Hydroastatic acid. Sometimes these words can be really hard to break down, but look for where the prefixes and the suffix are. That can really help you. So the hydro and the ic are there. If I'm thinking about like what kind of acid this is, when it starts with hydro, that's a different section of the flow chart than where we were just looking. So hydro and that suffix ic, when they're together, that's from our binary acid part of the flow chart. So I need to figure out what is that other element from the root that's in the blank, because this must be a binary acid. I mean, I've got the word acid there again. So having the word acid there already tells me that I need to be starting with an H, but I need to figure out what is this astat? What is this astat? Why did we put this problem on here? Why did we do this to ourselves? Okay, we need to figure out what is this astat that's going in this blank. So we need to find an element that the root of the element is a stat. And looking at your periodic table, I will point out that it's going to have to be a nonmetal. So you can restrict your search just to the right side over there. There is an element that works for. That element is astatine, which is right here. And it's AT. And again, this is going way back to December, but we're going to have to charge balance this, which means it's time to remember, at least for these anion families, what the charges are. Astatine's a halogen, so it's got a -1 charge. So we know we're having an H with a +1 and an AS with a -1. Having just one of each, the pluses and minuses can balance each other out. So our formula for hydroastatic acid is just HAS. It was sloppy. Here you go. That's your acid formula for this. Again, we saw the hydro and we knew that that prefix hydro only goes on a binary acid. So we knew we were looking for one other element, and we used that root, a stat, to find what was our single missing element that goes with hydrogen. Let's try some bases. So that's the other side of this chart. If you did hot dog fold your paper, you could still sort of more easily see the flow chart and the problems at the same time with the hot dog fold, if that's the way you want it to do. Okay. We're going to start with the CSOH. Bases are actually very easy to name, which is, we got that going for us. So we're gonna do this first one, CSOH. Does it start with an H? No, it does not. Does it end with an OH? Yes, it does. That makes it a base. Bases, you don't actually have to write the word base in your name of your base. You have a metal name and then you write the word hydroxide. So like, again, the problem we're looking at right now is CSOH. Hydroxide is the name of that OH, right? We talked about this at the top of the page. We also have hydroxide on our ion chart. It's on there. That's its name, hydroxide. So we're really just writing the name of the metal and then the word hydroxide. So the name of the metal, CS, is cesium. And then the name of that ion is hydroxide. And that's how you name the metal. That's it. That's how you name the base. I mean, that's all we got. So we have one little piece left. So that's our base. That's how you name the base. We only have one thing left here at the bottom of the page to worry about on this page anyway. And actually, this is the next page. Sorry, I got confused with the way I pasted these together. JK, we have a whole page left. We're now looking, if you're looking at this video in spring of 2022, I'm now on page 79, and we're going to talk about dissociation. Oh, sorry. Okay. Yeah, she's in a meeting right now. Okay. So we're separating acids and bases because when they dissolve in water, they separate themselves, actually. And that's where dissociation means separation. So you get your hydrogen and your chlorine. This is an acid, which I know because it starts with an H. And when this dissociates in water, or excuse me, when it dissolves in water, it dissociates, it breaks apart. The H turns into H+, which then finds a water molecule, and those combine to make hydronium, which we kind of talked about on the previous page. The thing is that some acids and bases break up really well, and some of them do not. And we have words for this. We call this strong and weak. So like in chemistry, the words strong and weak do not mean what you would think they mean in a lot of other contexts. Strong means they break apart really fully. So like a strong acid dissociation is complete. It fully dissociates 100% separation. Versus a weak acid is partial dissociation. It's less than 100% and usually way, way, way less than 100%. So you have some of them breaking up, but not most of them breaking up. We can see this with, hang on a second. Wrong button. Okay, we can see this with this simulation. You got your pure water. Some of it breaks up into hydroxide and hydronium, but not very much of it. And then a strong acid, though, all of it breaks up into the H+, which then becomes hydronium with water, and then whatever the leftover anion is. But a weak acid, some of it breaks up, and a lot of it stays the acid. So if you're looking at this little like key at the bottom here, like this is your starter acid, and most of what's dissolved in the water is still the starter acid, and very little of it is the hydronium and the acid anion. So you can see the same thing for a strong base. For a strong base, all of it breaks up. But for a like all of it is broken up into the ions. It's all dissociated. But for a weak base, most of what you have at the end is the original base, and very little of it has broken up into the ions comparatively. So what we do find is that strong acids will conduct a lot of electricity because there's a lot of ions in there. And if you remember from Unit 11, when ions are dissolved in water, they can conduct electricity because that moving charge is what actually conducts the current. A weak acid can conduct electricity, but like not as well. You can see that there's a lot more. This is like symbolized in this simulation. More light coming from the light bulb because more electricity from a strong acid versus a weak acid. Weak base, similarly, less amount of electricity. Strong base, more amount of electricity. So we find that when you're talking about a weak or strong acid and a weak or strong base, we can have similar discussions there. So an acid will completely dissociate if it is strong. It will partially dissociate if it is weak. But either way, because it is an acid, it's going to make H3O plus, the hydronium. So the acid part is what tells us it makes H3O plus. The strong and weak part is what tells us if it's complete or if it's partial. What does this mean? Will it conduct electricity? Yes, because there are some charges dissolved in there. But if it's strong, that's going to make a lot of ions when it's strong. And that means a light bulb would light up very brightly. So again, the word strong is what tells us that there are many ions. It's strong and it's bright. Versus a weak acid, yes, it will still conduct electricity, but because it is weak, there will be few ions. And because it is weak, that's what weak means. And that means the light bulb will be dimmer because there are few ions. So the word strong and the word weak tell us specifically how many ions are dissolved in there. I know, again, that this is like a kind of confusing way to talk about the word strong and the word weak. That's not normally what we think of when we think of the word strong and the word weak. But what we're saying is that like strong acids break up and then they stay broken up because they're like too strong to like fall back into the trap of a toxic relationship and get back together. Partial dissociation happens when they're weak because they break up and then they like change their mind, they get back together, and then they break up and then they're like, no, but I miss you, and then they get back together and then they break up again because the relationship's toxic and they're like, but oh, we were so happy. You were never happy, but you get back together anyway. Your strong acids and bases are like Taylor Swift. When she breaks up, it's complete, right? We are never, ever, ever getting back together. It's complete. A strong breakup is a complete breakup. It's a Taylor Swift breakup. They're fully, completely dissociated. They're not getting back together like ever. So that's what you can think of, your complete dissociation, your strong dissociation. That's your Taylor Swift breakup. So when we start talking about it in terms of bases, we're going to find the same thing. The word strong is what tells me that this is a complete 100% dissociation. And then the word weak is what tells me that this is a partial dissociation. Less than 100% of it, usually way less than 100% of it, breaks up. The word base is what's going to tell me, though, that what it makes when it's dissolved in water is hydroxide. Because it's a base, it makes hydroxide. Okay, the word base tells me that it's going to make hydroxide but the word strong tells me it breaks up completely. The word weak tells me it breaks up partially. So will they conduct electricity dissolved in water? Yes, because you have some ions in there. Having ions dissolved in water is what makes it conduct electricity. It's an electrolyte. But because it is strong or complete, I know that strong, it tells me there's going to be many ions and it's going to be bright. Versus the word weak is what tells me that there's going to be few ions and the light bulb would be dim. So this brings us to being able to label stuff. There are some steps to doing this labeling. The steps are there to make your life easier, so I advise you to read the steps. It says on the reactant side, the left side of the arrow, you're going to start by labeling the water. So go find the water. Oh, look, here it is, H2O. Okay, and you can do that on number 2 also. The water is down here for H2O. Then it says on the reactant side, the left side, label the other reactant as an acid or a base. So in number 1, we're starting with an H. So this is an acid. Versus in number 2, we're starting with a compound that ends in OH. So that makes this one a base. Okay, then it says on the product side, so we're switching now to the right side of the arrow, label if you have hydroxide or hydronium. You're only going to have one or the other. Okay, so I know like these are the ones I'm labeling. I do have to know which one's which. If you're not sure which one's which, I'll remind you that that chart that's in the back of your book, and it's also on the back of your periodic table whenever you're taking a quiz or a test in my class, hydroxide is on there. You don't have to memorize it. Hydroxide's on there. So that one, match it. That one's hydroxide. And you can copy the name from the chart. And then this other one must be hydronium. And if you forgot how to spell it, well, lucky for you, I literally wrote it out in front of you in the instructions. So this one's hydronium. We have 2 leftover boxes and no more instructions. So guess what? Those boxes are traps. They're trying to trick you. Cross the box out. We're not labeling that. There's no instructions to label it. Okay, that's acids and bases. Day 1. You have a quiz next class if you're watching this in spring 2022. So good luck.